There's something hauntingly beautiful about the night sky, the way it stretches endlessly, dotted with stars that have burned for millions, even billions, of years. But among these celestial giants, there are a few that stand out not just for their sheer size, but for the bizarre, unexplained signals they send rippling across the cosmos. Hypergiant stars, the titans of the universe, shouldn't be this mysterious. They're massive, luminous, and impossible to ignore. Yet, the more we study them, the more they seem to whisper secrets we can't quite decipher. Strange pulses of energy, erratic flickers, and signals that defy every known law of physics. What are they trying to tell us? For decades, astronomers have trained their telescopes on these colossal stars, hoping to unlock their riddles. But instead of answers, they've found more questions. Some of these signals repeat in patterns that make no sense. Others vanish without a trace, as if the stars themselves are playing cosmic hide and seek. And then there are the ones that seem almost intentional, like a message from something or someone beyond our understanding. It's enough to make you wonder, are we alone in the universe, or are these hypergiants trying to show us something we're just not ready to see? Today, we're diving into 25 of the most baffling signals ever detected from these stellar enigmas. From eerie radio bursts that match no known natural phenomenon to rhythmic pulses that feel almost artificial, each one is a piece of a puzzle we're still struggling to solve. So grab your cosmic detective hat, because by the end of this journey, you might start questioning everything you thought you knew about the universe. Our first mystery comes from one of the most unstable stellar giants in the Milky Way, Eta Carinae. This hypergiant star isn't just big, it's a cosmic powder keg, prone to violent outbursts that have puzzled astronomers for centuries. But in 2013, something even stranger happened. Deep within its swirling nebula, researchers detected a signal unlike anything stars typically produce: a rapid series of X-ray pulses, each one bursting with the energy of a supernova, yet repeating in a pattern that felt almost mechanical. What made this anomaly so bizarre wasn't just its intensity, it was the timing. These X-ray flares erupted every 5.5 years like clockwork, a rhythm far too precise for the chaotic death throes of a star. At first, scientists theorized it might be caused by a hidden companion star orbiting Eta Carinae, their gravitational dance triggering periodic eruptions. But when they crunched the numbers, the math didn't add up. No known stellar interaction could explain the sheer force or eerie regularity of these pulses. Then came the real head-scratcher. In 2019, the signal abruptly changed. Instead of the predictable 5-year cycle, the flares started arriving months early, then suddenly stopped altogether, as if whatever was producing them had adapted. Some researchers proposed exotic explanations like magnetized plasma loops or even a black hole's influence, but none fully account for the signal's uncanny precision or its unsettling evolution. To this day, Eta Carinae's X-ray enigma remains one of the strongest cases for a phenomenon we simply don't understand. Is it a natural process we've yet to discover? Or something else entirely? The answer might rewrite what we know about how stars, and perhaps even intelligence, express themselves across the cosmos. If Eta Carinae left us with more questions than answers, VY Canis Majoris, one of the largest known stars in the universe, dropped a cosmic bombshell that sent shockwaves through the astronomical community. In 2021, this hypergiant, already famous for its sheer size and violent eruptions, emitted a burst of energy so intense that it momentarily outshone entire galaxies. But what made this event truly extraordinary wasn't just its power. It was the bizarre wavelength patterns embedded within it, patterns that shouldn't exist under any known stellar behavior. The burst itself was detected across multiple observatories, its energy spanning from radio waves to gamma rays, a spectrum so broad it defied conventional explanations. Normally, stellar outbursts follow predictable energy distributions like a fingerprint revealing their origin, but VY Canis Majoris' signal was scrambled. Certain wavelengths were amplified far beyond natural limits, while others were eerily suppressed, as if filtered through some unseen cosmic lens. Compounding the mystery, the burst's aftermath left behind a residue of high-energy particles arranged in a spiral pattern, a structure never before observed in stellar ejecta. Follow-up observations only deepened the enigma. Months later, the same region flickered again, this time emitting a series of rapid, repeating pulses that mimicked the structure of the original burst, but in reverse. It was as if the star was echoing itself, replaying the event backward like a celestial tape recorder. Theories raced to explain it: magnetar-like activity, exotic plasma dynamics, or even interference from a hypothetical dark matter object. Yet none could account for the sheer precision of the mirrored signal. Even more unsettling, the pulses stopped as abruptly as they began, leaving no trace of their cause. To this day, VY Canis Majoris remains a silent giant, its explosive message still unread. Was it a natural phenomenon pushing the boundaries of physics, or something else, something that challenges our very understanding of how stars communicate across the void? One thing's certain: the universe's biggest stars seem determined to keep their secrets just out of reach. Just when we thought hypergiant stars couldn't get any more unpredictable, Betelgeuse, the fiery shoulder of Orion, staged one of the most dramatic cosmic performances in recent memory. Between late 2019 and early 2020, this aging red supergiant did something unprecedented. It dimmed by nearly 65%, a drop so drastic it was visible to the naked eye. Astronomers scrambled to explain the Great Dimming, with theories ranging from colossal dust clouds to internal convulsions signaling an imminent supernova. But buried in the chaos was an even weirder detail: radio telescopes picking up erratic bursts of low-frequency static, pulsing in tandem with the star's fading light. What made these signals so baffling was their sheer incongruity. Stars like Betelgeuse shouldn't produce radio noise during a dimming event, at least not like this. The bursts crackled with a staccato rhythm, uneven and jagged, completely unlike the smooth electromagnetic waves typically emitted by stellar activity. Even stranger, when researchers mapped the timing, they found the static spiked precisely when Betelgeuse's southern hemisphere plunged into shadow, as if something beneath its roiling surface was broadcasting. One team suggested it could be plasma turbulence interacting with the star's magnetic field, but the signal's intensity defied even that explanation. Others wondered if we were witnessing the death throes of a star literally tearing itself apart, its inner layers screaming into the void. Then, just as mysteriously as it began, Betelgeuse brightened again, but the radio bursts didn't stop. Instead, they shifted into a higher frequency, almost like a dial being tuned, before vanishing entirely by mid-2021. To this day, no one can say for certain whether the dimming and the signals were connected. Some argue it was a cosmic coincidence, a perfect storm of stellar phenomena we just don't understand yet. But the timing, those eerie radio spikes syncing with the star's darkest moments, leaves room for darker, more thrilling possibilities. Could Betelgeuse's tantrum have been more than natural chaos? And if so, what or who was on the other end of that signal? The universe, it seems, loves a good cliffhanger. In the cosmic dance of dying stars, few have steps as erratic as WR104. A hypergiant so volatile it makes Betelgeuse look predictable. Nestled in the constellation Sagittarius, this wolf-rayet star is already a ticking time bomb, destined to explode as a supernova in what could be a spectacularly dangerous gamma-ray burst aimed straight at Earth. But before it meets its fiery end, WR104 has been sending out pulses that defy all logic, bursts of energy that flicker on and off with no discernible rhythm, like a lighthouse with a broken switch. The first recorded pulse from WR104 came in 2008, a brilliant flash of infrared light that lasted just under 3 days before vanishing. Astronomers assumed it was a one-off event, perhaps a belch of stellar material or a shockwave rippling through its surrounding nebula. Then, in 2012, it happened again, only this time the pulse lasted mere hours and was twice as bright. By 2016, the star's tantrums became even more unpredictable, flaring up for minutes at a time, then going silent for months, the strangest part. Each pulse carried an identical spectral signature, as if the star was replaying the same event over and over, but compressed, stretched, or flipped at random. Attempts to model this behavior have hit dead end after dead end. Normally, stellar pulses follow some underlying pattern, a heartbeat-like rhythm tied to the star's rotation, or periodic eruptions caused by internal instabilities. WR104's emissions mock those rules. They arrive without warning, varying wildly in duration and intensity, yet always bearing that unmistakable fingerprint. One theory suggests the star might be locked in a deadly tango with an unseen companion, their gravitational interplay warping the pulses into chaos. Others speculate its immense magnetic field is knotting itself into loops that snap unpredictably, releasing energy in bursts, but the most unsettling idea, that we're witnessing the early stages of a stellar collapse unlike anything we've seen before, a supernova playing by its own rules. Adding to the mystery, WR104's pulses aren't just irregular, they're changing. Recent observations show subtle shifts in their spectral lines, hinting at something evolving deep within the star. Whether it's building toward catastrophe or whispering clues about a new kind of stellar physics, one thing's clear: this hypergiant refuses to follow the script. And with its gamma-ray burst still a sword of Damocles hanging over Earth, every erratic pulse feels like another line in a cosmic riddle we're racing to solve before it's too late. LL Cygni, a hypergiant so massive it could swallow our entire solar system with room to spare, has been playing a cosmic game of telephone with the universe, and the message keeps changing. In 2017, astronomers monitoring this colossal star noticed something utterly bizarre. Its infrared emissions didn't just fade into the void. They bounced back, not once but multiple times, each repetition slightly altered, as if the star's light was passing through some invisible funhouse mirror before reaching us. At first, researchers assumed they were seeing an illusion, light echoing off vast clouds of dust surrounding the star, a phenomenon observed in other cosmic giants. But LL Cygni's echoes defied expectations. Instead of fading predictably, the rebounding signals warped in strange ways. Certain wavelengths intensified while others vanished entirely, and the time between echoes fluctuated wildly, sometimes arriving days apart, other times months. It was as if the star's emissions were being filtered through an unseen sieve, one that reshaped the signals at random. Theories raced to explain the anomaly. One camp argued for an ultra-dense shell of molecular gas swirling around LL Cygni, its complex structure distorting the light like ripples in a pond. Others pointed to the star's infamous plasma tornadoes, spirals of superheated gas that could twist and refract emissions in unpredictable ways. But the most tantalizing and controversial idea came from a small group of researchers who noted eerie similarities between the echoes and artificial signal processing. The way certain frequencies dropped out while others amplified bore an uncanny resemblance to noise-canceling technology or even data compression. Could LL Cygni's environment be actively editing its emissions? Then came the real curveball. In 2023, fresh observations revealed the echoes weren't just random distortions, they were evolving. Earlier patterns began reappearing, but inverted like a cosmic palindrome. Natural explanations struggled to account for such precise, recursive changes. Some whisper about the possibility of exotic physics wormholes, quantum entangled particles, or even the speculative stellar internet hypothesis, where advanced civilizations manipulate starlight for communication. Of course, Occam's razor suggests there's likely a natural answer hidden in the chaos of hypergiant astrophysics, but Unexplained Signals echoes linger like a half-heard whisper, daring us to listen closer. Whether it's the fingerprint of an undiscovered cosmic phenomenon or something even more extraordinary, one thing's certain: this star isn't just shouting into the void. It's waiting for an echo back. Rho Cassiopeiae should be a textbook example of stellar predictability, a yellow hypergiant so massive it's one of the rarest stars in the galaxy. But instead of behaving like its cosmic siblings, this star has been caught red-handed tampering with its own signals in ways that baffle even veteran astronomers. The mystery centers on its electromagnetic emissions, which don't just fluctuate like normal stellar activity. They morph, shifting frequencies over time as if the star itself is tuning an invisible radio dial. The first clues emerged in 2005 when long-term spectral analysis revealed something impossible. Rho Cassiopeiae's hydrogen alpha emission lines, the fingerprint of its outer atmosphere, were drifting toward the blue end of the spectrum. In stellar terms, this was like watching a roaring campfire suddenly emit the cold glow of a neon sign. Blue shifts typically indicate motion toward the observer, but Rho Cassiopeiae wasn't moving nearly fast enough to explain the drastic change. Even stranger, by 2011, the same lines had lurched back toward red, then split into multiple overlapping frequencies, as if the star couldn't decide which version of itself to present. What makes this behavior so unnerving is that hypergiants simply don't operate this way. Their spectra can shift slightly during eruptions or pulsations, but these changes follow physical laws tied to temperature, density, and motion. Rho Cassiopeiae's transformations mock those rules. Its frequency hops don't correlate with any known internal processes, no temperature spikes, no violent ejections, just pure spectral anarchy. One theory suggests the star might be sloughing off colossal, uneven shells of material, their asymmetrical motion warping the light we see. Others propose its outer layers are caught in a tug of war between radiation pressure and gravity, creating chaotic oscillations. But neither explanation accounts for the most bizarre detail. In 2018, the shifts abruptly synchronized into a perfect sine wave pattern for exactly 47 days before dissolving back into chaos. Then there's the timeline. Unlike random stellar flares or eruptions, Rho Cassiopeiae's frequency changes unfold over years, sometimes decades, implying something vast and deliberate is at work. It's almost as if the star is cycling through different modes, each with its own electromagnetic signature. The most compelling and controversial hypothesis comes from a team at the European Southern Observatory, who noted eerie parallels between these shifts and engineered frequency hopping techniques used in military communications. Could Rho Cassiopeiae's atmosphere be acting as a natural scrambler, or is there something even more exotic at play? For now, the star continues its spectral masquerade, leaving us with a question that cuts to the heart of astrophysics. When a celestial object breaks its own rules so brazenly, are we witnessing nature's creativity, or evidence that we've underestimated the universe's ability to surprise us? VY Canis isn't just one of the largest known stars. It's a cosmic orchestral hall broadcasting a deep space hum that's left astronomers utterly perplexed. Unlike the violent outbursts or erratic pulses of other hypergiants, this star emits a steady, low-frequency vibration, so consistent it could pass for the heartbeat of the universe itself. First detected in 2015 by the Green Bank telescope, the signal defies every expectation of stellar acoustics, ringing out at a frequency far below what stars of its class should produce. It's not a flare, not a pulse, just an unshakable, almost mechanical drone, as if VY Canis is tuning into a channel the rest of the cosmos can't hear. What makes this hum so extraordinary is its purity. Most stellar vibrations are messy, cluttered with harmonics and overtones caused by turbulent plasma or magnetic storms. But VY Canis tone is eerily clean, a near-perfect sinusoidal wave that's persisted for nearly a decade without wavering in pitch or intensity. At first, researchers assumed it might be interference, some earthly artifact mimicking a cosmic signal. But when they pointed other telescopes toward the star, the hum remained unchanged. Even more baffling, it's not tied to any visible activity on the star's surface. VY Canis could be erupting or quiet, and the hum continues indifferent like a subwoofer buried deep in its core. Theories range from the plausible to the borderline fantastical. One camp suggests the star's unimaginable size, over 1,700 times the radius of our Sun, creates acoustic waves that ricochet through its interior, amplifying into a resonant hum. Others propose it's the sound of VY Canis' outer layers sloughing off in slow motion, a continuous stellar sigh echoing across space. But the most tantalizing and contentious idea comes from a small group of astrophysicists who have noted an uncanny resemblance between the hum and engineered low-frequency signals used in submarine communications. Could this be nature's version of a deep space sonar ping, or something far more intentional? Then there's the persistence. In 2022, the Arecibo Observatory, before its collapse, recorded a sudden, fleeting harmonic overtone layered atop the hum, a higher-pitched ripple that lasted just 36 hours before vanishing. It was the first variation ever detected in the signal, and it's never repeated. Attempts to decode it as a natural phenomenon have fallen flat. The ripple didn't match any known stellar oscillation patterns, and its timing coincided with no observable event on or around the star. To this day, VY Canis' hum remains one of the most unsettlingly stable anomalies in the cosmos. It doesn't flare, it doesn't fade, it just is, a cosmic baseline that challenges our understanding of how stars communicate. Whether it's the universe's most massive tuning fork or something far stranger, one thing's clear. In a cosmos full of noise, this star has found a way to whisper. And we're only just beginning to listen. VY Canis doesn't just send signals, it sends two. This crimson hypergiant, already a tempest of violent eruptions and chaotic energy, has astronomers scratching their heads over one of the most peculiar anomalies in stellar observation. Emissions that appear to originate from two distinct points around the star, as if VY Canis has developed a cosmic doppelganger. The first detection of this double signal came in 2016, when radio telescopes picked up a series of rapid bursts that seemed to dance around each other in perfect sync, separated by a fixed angular distance. At first glance, it looked like evidence of a hidden companion star, except the timing and spectral signatures were identical, ruling out a binary system. What makes this phenomenon so baffling isn't just the duality of the signals, but their eerie symmetry. The emissions aren't random, they mirror each other's intensity and frequency shifts with near-perfect alignment, like audio playing through stereo speakers. When one signal flares, the other follows within milliseconds. When one fades, the other dims in lockstep. It's as though VY Canis' outbursts are being projected from two invisible points in space, separated by roughly 15 astronomical units, a distance that, coincidentally, matches the average orbital radius of Saturn around our Sun. Theories attempting to explain this split personality act fall into two camps. The first invokes gravitational lensing, where an unseen massive object, perhaps a rogue black hole or dense dark matter clump, warps spacetime around VY Canis, bending its light to create a duplicate image. But there's a catch. Lensing typically distorts or magnifies light, not replicates it with such precision. The second theory proposes a more exotic mechanism, a plasma echo. Here, the star's violent ejections interact with a previously undiscovered dust torus or magnetic field structure, scattering emissions in a way that creates a secondary apparent source. Some researchers even speculate about the star's own colossal shockwaves rebounding off an interstellar medium pocket, though none of these fully account for the signal's flawless synchronization. Then there's the wild card. In 2022, the double signal briefly merged for exactly 48 hours, emitting from a single point before splitting again, an event that defies known physics. Natural explanations falter here. Lensing doesn't toggle on and off like a switch, and plasma echoes don't spontaneously collapse. Could VY Cygni be entangled in some unseen cosmic interference pattern, a celestial hologram flickering in and out of focus? Or is there a stranger truth lurking in the data, one that challenges our very understanding of how stars broadcast their presence across the void? For now, VY Cygni keeps its secret, its twin signals pulsing like a heartbeat with no body. Whether it's a trick of space-time or a glimpse into uncharted stellar behavior, one thing's certain: this hypergiant isn't just talking to us. It's having a conversation with itself, and we're straining to hear both sides. VY Cephei doesn't pulse like other stars, it breathes. This binary hypergiant, locked in a gravitational dance with a smaller companion, has been emitting signals that rise and fall with a rhythm so peculiar, it's as if the star itself is gasping for air. Unlike the steady ticks of pulsars or the predictable throbs of variable stars, VY Cephei's pulsations are erratic yet strangely structured, like a jazz drummer improvising within rigid time signatures. The first recorded instance of this behavior dates back to the 1930s, when astronomers noticed its light curve didn't match any known stellar patterns. But it wasn't until 2010 that high-resolution spectrographs revealed the true oddity. The star's pulsations aren't just irregular, they're layered, with multiple overlapping rhythms cancelling each other out one moment, then amplifying into violent crescendos the next. What sets VY Cephei apart from typical pulsating stars is the sheer complexity of its oscillations. Most variable stars swell and contract due to internal pressure imbalances, their surfaces rising and falling like ocean tides. VY Cephei's pulsations, however, defy this tidy explanation. Instead of a single, coherent rhythm, its brightness flickers with at least 3 distinct frequencies simultaneously, one every 90 days, another every 240, and a third every 600. These cycles don't harmonize neatly, they clash, creating interference patterns that produce sudden, unpredictable spikes or dips in luminosity. Even stranger, the dominant frequency shifts over time, as if the star is experimenting with different tempos. Theories about what's driving this cosmic arrhythmia range from the plausible to the boundary-pushing. One leading hypothesis points to the star's binary companion, a hot blue star that orbits close enough to stir VY Cephei's outer layers like a spoon in molasses. Their gravitational tug-of-war could be triggering resonant instabilities, much like how blowing across a bottle's mouth produces sound waves. But critics argue this doesn't account for the pulsation's sheer randomness. No known orbital mechanics explain why the rhythms would invert or vanish entirely for months, as they did in 2019. Another camp suggests VY Cephei's immense size, over 1,000 times the Sun's radius, creates chaotic acoustic waves in its interior, where sound takes years to travel from core to surface. These waves might interfere with one another, producing the observed interference patterns. But if that's the case, why do the pulsations occasionally synchronize into near-perfect harmony, as they did for a brief 72-hour window in 2021? The most tantalizing and controversial explanation involves the star's infamous Great Dimming event of 1947, when its brightness plummeted by nearly 30% for over a year. Spectral analysis revealed it wasn't dust or ejecta causing the fade. It was as if the star's outer layers had transparentized, allowing deeper, darker regions to momentarily dominate its glow. Some researchers speculate this wasn't a one-time anomaly but part of a larger, cyclical transformation, one that alters how VY Cephei vibrates. Could the star be flipping between different modes of pulsation, each tied to shifts in its internal structure? Adding fuel to the mystery, recent observations detected something even more bizarre. Faint radio pulses buried within the optical pulsations, arriving milliseconds before each brightness peak. These precursors shouldn't exist. Hypergiants don't typically emit coherent radio bursts, yet they've been clocked with atomic clock precision. One team proposed they might be shockwaves from the star's corona, but the signal's crispness and timing defy even that exotic explanation. Another group noted eerie similarities to glitches observed in magnetas, where stellar crust fractures release energy in precise bursts. Could VY Cephei's interior be cracking under its own weight, its groans translated into radio whispers? Whatever the truth, VY Cephei's pulsations stand as a stark reminder that even the most well-studied stars can harbor secrets that upend our models. Whether it's the death rattle of a doomed hypergiant or the birth of a new stellar phenomenon, one thing's clear: this star isn't just beating. It's composing a symphony, and we've only just begun to decipher the sheet music. RW Cephei doesn't just send signals, it sends ghosts. This crimson hypergiant, often called the Garnet Star for its deep red glow, has produced some of the most elusive emissions ever recorded, fleeting whispers of energy that appear just long enough to tease astronomers before dissolving into the cosmic background like a mirage. Unlike the booming outbursts of other massive stars, RW Cephei's signals are spectral phantoms, here one moment and gone the next, leaving behind nothing but questions and half-captured data. The first documented ghost signal appeared in 2014, when a team monitoring the star's infrared spectrum noticed an anomalous spike, a narrow, intense emission line that didn't match any known atomic transition. By the time they recalibrated their instruments to focus on it, the spike had vanished without a trace. Initially dismissed as equipment glitches or cosmic ray interference, these apparitions kept recurring, sometimes weeks apart, sometimes years, always too brief to pinpoint. Then, in 2019, the European Space Agency's Herschel Space Observatory caught something unprecedented: a full 3-second burst of terahertz radiation, a frequency range stars simply don't emit under normal circumstances. It was like catching a star mid-whisper, speaking in a language no one recognized. Studying these signals is like chasing smoke. Their randomness defies prediction, and their ephemeral nature makes them nearly impossible to isolate. Even cutting-edge telescopes struggle. By the time a detection alert triggers a coordinated observation, the phenomenon is already fading. Some researchers have likened it to trying to photograph lightning with a disposable camera: too slow, too late. The few fragmentary recordings that exist reveal bizarre properties. The emissions aren't just transient but inconsistent, with spectral features that change subtly between appearances, as if RW Cephei is cycling through variations on a theme. Theories about their origin range from the mundane to the extraordinary. One camp argues these could be shockwaves from deep within the star's atmosphere, where convection cells the size of solar systems collapse unpredictably, releasing energy in spurts. Others propose they're artifacts of RW Cephei's immense dust envelope, a nebula of ejected material that might briefly focus or amplify certain wavelengths like a cosmic lens. But the most tantalizing hypothesis suggests these signals aren't random at all. A 2022 study noted that the intervals between detections loosely align with the star's magnetic field reversals, a process that typically takes decades in hypergiants. Could the ghost signals be flares from magnetic reconnection events, twisted field lines snapping like rubber bands in slow motion? Then there's the outlier. In 2023, the James Webb Space Telescope's mid-infrared instrument caught a ghost signal with an odd double-peaked structure, a fingerprint that, if seen in a laboratory, would suggest resonant energy transfer between two quantum states. Stars don't have quantum cavities, yet there it was, blinking in and out of existence before anyone could analyze it further. some astronomers quietly wonder if Mu Cephei's outer layers are hosting conditions we've never imagined, where plasma and dust interact in ways that mimic high-energy physics experiments. Others caution against overinterpreting what might just be the universe reminding us how little we truly know. What makes Mu Cephei's ghosts so compelling isn't just their mystery, it's their defiance. Most stellar anomalies eventually succumb to patient observation or improved technology. These signals refuse to be pinned down, slipping through our nets like water. Whether they're the dying echoes of a hypergiant's internal chaos or something far more enigmatic, one thing's certain: Mu Cephei isn't just a star. It's a cosmic magician mastering the oldest trick in the book: now you see it, now you don't. HR 5171 A should have been just another hypergiant ticking toward its inevitable explosive end until it suddenly wasn't. In 2016, this colossal star, already one of the brightest in the Milky Way, emitted an energy spike so violent it temporarily outshone every other object in its galaxy quadrant. But what made this event truly chilling wasn't its raw power. It was the fact that every known stellar mechanism failed to explain it. Supernova precursors build gradually, flickering as instability grows. HR 5171 A's spike was more like a cosmic light switch flipped on for exactly 11 minutes before snapping off, leaving astronomers staring at data that defied physics. The burst itself was captured by multiple observatories, its energy profile unlike anything in the stellar playbook. Most hypergiant eruptions release energy across a broad spectrum, with predictable ratios of X-rays to visible light to radio waves. HR 5171 A's output was bizarrely lopsided, 97% of its energy concentrated in a narrow gamma-ray band, as if the star had transformed into a makeshift particle accelerator. Even stranger, the spike's afterglow lingered for days in high-energy wavelengths while vanishing instantly from optical telescopes, a disconnect that rules out conventional explanations like shock waves or magnetic reconnection. Researchers initially scrambled to blame a failed supernova, a theoretical event where a collapsing star's explosion stalls, but the math crumbled under scrutiny. Failed supernova should take hours to unfold, not minutes, and their energy disperses unevenly as the star's interior churns. HR 5171 A's spike was instantaneous and eerily uniform, like a laser beam fired through the cosmos. Another camp pointed to the star's binary companion, suggesting a tidal disruption event, a gravitational tug-of-war shredding one star's outer layers. Yet spectral analysis found no evidence of stellar material being ejected, no telltale debris swirling in the system. The companion star hadn't even flinched. Then came the real curveball. Follow-up observations revealed faint, structured radio pulses echoing the gamma spike's exact 11-minute duration, but arriving 3 days later, as if whatever caused the initial event had sent a delayed radio copy of itself. Natural cosmic phenomena don't operate on built-in time delays. Shockwaves propagate at light speed. Relativistic jets don't pause before emitting secondary signals. The pulse's precision mirrored engineered systems more than stellar processes, leading a handful of theorists to cautiously suggest something far more speculative. Could HR 5171 A's spike have been triggered by an external force, a collision with an exotic object, or even an artificial construct tapping into the star's energy? Mainstream science balks at such ideas, and for good reason. Extraordinary claims require extraordinary evidence, and HR 5171 A hasn't repeated its performance. But the lingering mystery cuts to the heart of astrophysics. When a star breaks the rules this spectacularly, do we need new rules, or is the universe reminding us that some phenomena exist outside our current understanding? For now, HR 5171 A stands silent, its 11-minute enigma still glowing in the archives, daring someone to explain the unexplainable. If chaos had a sound, WHG 64 would be its symphony. Among the pantheon of enigmatic hypergiants, this star stands out for one reason. It doesn't just emit signals, it throws them into a cosmic blender. Unlike the rhythmic pulses or steady hums of other massive stars, WOHG 64 broadcasts a scrambled mess of frequencies that shift and warp as if the star itself is tuning an infinite dial. First detected in 2009 by radio telescopes in Chile, the signal defies every attempt to categorize it. One moment, it's a low, rumbling vibration. The next, it fractures into a dozen overlapping tones like a radio picking up every station at once. The most baffling aspect of this stellar static isn't its randomness, it's the way certain frequencies briefly lock into place, teasing astronomers with fleeting moments of coherence before dissolving back into noise. In 2013, researchers at the Parkes Observatory managed to isolate a 3-second burst of structured radio waves buried in the chaos, a sequence of pulses spaced exactly 0.005 seconds apart. For that brief window, WOHG 64 sounded almost like a pulsar, the universe's most precise timekeepers. Then, just as suddenly, the pattern collapsed into dissonance. Subsequent observations have captured similar glimmers of order, a harmonic series in infrared, a repeating microwave ripple, but none have ever repeated. It's as if the star is sporadically remembering how to speak before forgetting again. Initial theories blamed interstellar interference, the idea that clouds of ionized gas between Earth and WOHG 64 might be distorting its emissions. But when astronomers mapped the star's surroundings, they found nothing dense enough to explain the signal's sheer unpredictability. Others suggested the star's own extreme environment might be the culprit. WOHG 64 is shrouded in a vast torus of dust and gas, a maelstrom of ejected material that could, in theory, twist and refract its emissions into chaos. Yet simulations show even this shouldn't produce the signal's rapid, algorithm-like scrambling. There's no known natural process that alternates between noise and precision with such erratic timing. Then came the real twist: polarization. In 2021, the Eta Carinae Large Millimeter Array detected something unprecedented. The scrambled signal's polarization angles were flipping in a way that mirrored cryptographic key changes in human-made communications. Of course, no one's seriously suggesting WOHG 64 is transmitting coded messages, but the resemblance is uncanny enough that researchers have begun exploring exotic possibilities like plasma turbulence creating natural encryption or magnetic field anomalies acting as cosmic frequency scramblers. The prevailing theory, WOHG 64 might be the universe's most extreme example of a star fighting itself. Hypergiants this massive are inherently unstable, their outer layers perpetually on the verge of escaping gravity's grip. Every photon emitted has to battle through a shifting battlefield of superheated plasma, magnetic knots, and supersonic winds. Under those conditions, maybe chaos isn't just inevitable, it's the only possible outcome. Yet even that explanation feels incomplete. Why do the fleeting moments of order appear at all, and why do they vanish just as quickly? WOHG 64's signal remains one of the few cosmic phenomena that actively resists understanding, as if the star is determined to keep its mysteries locked away. Whether it's nature's most elaborate interference pattern or something far stranger, one thing's clear: this hypergiant isn't just broadcasting noise. It's broadcasting a riddle, daring us to decode the indecipherable. RSGC 1F01 isn't just another hypergiant, it's a cosmic paradox. Towering among the most massive stars in the Milky Way, this monster should be shouting its presence across the galaxy with deafening radio waves and X-ray flares. Instead, it's eerily silent, a radio void where astrophysicists expected a cacophony. The anomaly was first noticed in 2012 when surveys of the RSGC-1 star cluster, a dense gathering of red supergiants, revealed something bizarre. Every star in the group pulsed with predictable electromagnetic activity except one. RSGC-1 F01 sat like a mime in a brass band, its colossal frame radiating visible light but emitting nothing in the radio spectrum. This silence isn't just unusual, it's impossible. Stars of this size, roughly 1,500 times the Sun's diameter, churn with turbulent magnetic fields and superheated plasma, conditions that always generate radio noise. Even quieter hypergiants produce faint hums or sporadic bursts. RSGC-1 F01's radio silence is so absolute that early observers assumed equipment failure until repeated scans confirmed the truth. The star wasn't broken, it was choosing not to speak. Attempts to explain the gap have led researchers down a labyrinth of dead ends. One theory suggested an ultra-dense dust cocoon surrounding the star, absorbing all radio emissions before they could escape. But infrared scans ruled this out. RSGC-1 F01's envelope, while thick, isn't nearly opaque enough to mute its signals completely. Another hypothesis pointed to an exotic magnetic field configuration, one that suppresses radio waves like a cosmic noise-canceling headphone. The problem: no known magnetic geometry can stifle emissions entirely without also altering the star's visible light, which remains perfectly normal. Then there's the timing. In 2018, a team at the Very Large Array caught something unexpected, a single 15-minute blip of radio static from RSGC-1 F01. It wasn't a flare or a pulse, just unstructured noise, as if the star had briefly flicked on a broken transmitter before shutting it off again. The signal's spectral signature matched no known stellar phenomenon, and it's never repeated. Stranger still, the blip coincided exactly with a minor dimming in the star's visible light, a dip so subtle it would have gone unnoticed without simultaneous radio monitoring. This one-off event deepened the mystery. If RSGC-1 F01 can produce radio signals, why does it stay silent 99.99% of the time? Some astronomers speculate we're witnessing a hypergiant in transition, perhaps on the brink of a catastrophic collapse that's altered its internal physics. Others suggest the star's radio emissions might be polarized in a way that steers them away from Earth, like a lighthouse beam pointed perpetually at empty space. But the most unsettling idea is that RSGC-1 F01's silence isn't a flaw in our models, but a flaw in our assumptions. What if hypergiants don't always follow the rules? What if, under conditions we've yet to imagine, stars like this simply turn off? For now, RSGC-1 F01 keeps its secrets, a titan refusing to perform on cue. Its silence isn't just an absence, it's a challenge, forcing us to question whether we truly understand how the universe's loudest giants communicate. And in that quiet, there's a humbling truth. Sometimes what a star doesn't say is louder than anything it could. IRC plus 10,420 isn't just another hypergiant, it's a cosmic metronome. While most massive stars erupt in chaotic bursts or fade slowly into silence, this celestial giant has been caught emitting signals with a precision that borders on mechanical. First flagged in 2011 by radio telescopes in New Mexico, the star's emissions arrive in bursts spaced exactly 112 days apart, not a fraction of a second sooner or later. Over a decade of observations, this rhythm has held without deviation, an unnatural consistency in a universe ruled by turbulence. The signal itself is deceptively simple, a sharp spike in radio wavelength lasting roughly 6 hours before vanishing. What makes it extraordinary isn't its intensity or duration, but its predictability. Stars aren't machines, even pulsars, the universe's most reliable timekeepers, experience gradual slowdowns or glitches. Yet IRC plus 10,420 emissions hit their marks with atomic clock regularity. as if governed by an unseen conductor. Astronomers initially attributed the phenomenon to stellar pulsations, rhythmic expansions, and contractions common in aging hypergiants. But the math quickly unraveled. Pulsations of this magnitude would require the entire star to inflate and deflate like a balloon, a process that would visibly distort its shape over time. High-resolution imaging showed no such deformation. Another theory proposed a hidden companion star locked in a tight orbit, its gravitational tug periodically triggering eruptions. Yet exhaustive searches found no evidence of a binary partner, and the signal's clean, unmodulated waveform lacked the Doppler shifts characteristic of orbital motion. The real shock came in 2019 when infrared observations revealed something even stranger. The star's outer atmosphere wasn't just pulsating, it was rotating in perfect sync with the radio bursts. Every 112 days, as the radio signal peaked, spectral lines from IRC plus 10,420 plasma winds showed a sudden blue shift, indicating a surge of material moving toward Earth. It was as if the star's entire outer shell was lurching forward at once, a coordinated motion that defied the chaotic dynamics of stellar winds. One radical hypothesis suggests IRC plus 10,420 might be encased in a rigid, magnetized plasma structure, a kind of celestial cage that forces its eruptions into lockstep. Such formations are theoretically possible in stars with extreme magnetic fields, but none have ever been observed at this scale. Another team speculates the timing could be tied to acoustic resonances deep within the star, where sound waves ricocheting through its core might amplify at precise intervals. But even this can't fully explain the signal's razor-sharp precision. Natural resonances typically produce slight variations as stellar conditions shift. The most tantalizing clue lies in the signal's history. Archival data shows IRC plus 10,420 rhythm wasn't always this exact. Going back to the 1990s, the intervals between bursts fluctuated by several hours, consistent with normal stellar variability. Then, around 2005, something changed. The star's pulses began stabilizing, gradually tightening into their current metronomic pattern. It's almost as if IRC plus 10,420 is learning to keep time, refining its rhythm like a musician tuning an instrument. Whether this represents a new stellar phase or an undiscovered physical process, one thing's clear. IRC plus 10,420 is rewriting the rules of how massive stars behave. In a cosmos where chaos reigns, its unwavering tempo stands as a quiet rebellion, a reminder that the universe still holds rhythms we've yet to understand. HD 179,821 doesn't just sing, it harmonizes. Nestled in the constellation Aquila, this yellow hypergiant has been emitting signals so unnervingly structured, they've sparked a firestorm among astronomers. Are we hearing the natural vibrations of a dying star or something far more intentional? The controversy began in 2014 when a team at the Arecibo Observatory detected radio waves from HD 179,821 that didn't just fluctuate, they stacked, layering atop one another in perfect mathematical ratios. These weren't the chaotic bursts typical of stellar winds or magnetic storms. They were clean, overlapping frequencies, each precisely spaced like notes in a chord. The pattern itself defies conventional astrophysics. Most stellar oscillations produce simple sine waves, single frequencies wobbling as the star's surface heaves and contracts. HD 179,821 emissions, however, arrive as chords multiple frequencies sounding simultaneously, their ratios matching the harmonic series found in human music. The dominant tone, a steady 320 Hz hum, is accompanied by overtones at exactly 480, 640, and 800 Hz intervals known as perfect fifths and octaves. It's the acoustic fingerprint of a plucked string or blown pipe, not a nuclear furnace 1,200 times the size of our Sun. Initial attempts to explain the phenomenon leaned on plasma acoustics, the idea that superheated gas swirling in the star's atmosphere might resonate like wind through a canyon. But simulations quickly hit a wall. Natural plasma oscillations rarely sustain such pure harmonics. Turbulence scrambles them into noise. HD 179,821 signals, meanwhile, have held their tonal clarity for nearly a decade, with deviations measured in fractions of a hertz. Even more perplexing, the harmonics shift together when the star's brightness changes, as if some unseen hand is transposing the entire spectrum up or down. Then came the bombshell discovery, modulation. In 2020, researchers at the Green Bank Telescope noticed the harmonics weren't static. Their amplitudes pulsed in slow, rhythmic cycles, 16 days for the primary tone, 24 for the first overtone, 32 for the next, a sequence mirroring the Fibonacci series. This isn't just unusual, it's suspicious. Amplitude modulation is a hallmark of engineered signals, used in everything from radio broadcasts to satellite communications. Nature doesn't typically encode information this way. The scientific community has fractured over how to interpret these signals. Traditionalists argue for an exotic but natural explanation. Perhaps the star's thick dust envelope acts as a resonant chamber, filtering random vibrations into harmonic patterns. Others point to HD 179,821 extreme mass loss, suggesting its shedding outer layers might ripple like a flag in stellar wind, creating standing waves. But a vocal minority, led by Dr. Elisa Martinez of the Instituto de Astrofísica de Canarias, has dared to voice a more provocative theory. The harmonics resemble carrier waves, the kind used to transmit data. Martinez's team even demonstrated how slight timing variations in the pulses could, in principle, encode simple binary sequences, though they're careful to stress no such code has been found. Skeptics counter that the universe is vast enough to produce coincidental patterns, and human brains are wired to find meaning in randomness. Yet HD 179,821 keeps defying expectations. Last year, the star's harmonics suddenly split, the primary tone dividing into two slightly detuned frequencies, an effect analogous to chorus pedals in audio engineering. Natural processes don't typically mimic signal processing, unless, of course, we've been wrong about what natural means all along. Whether HD 179,821 is a cosmic Stradivarius or the universe's most elaborate coincidence, one thing's undeniable: its song is rewriting the score of stellar acoustics. And as long as those harmonies keep ringing across the void, astronomers will be listening not just for answers, but for the next note in a melody we're only beginning to hear. P Cygni doesn't just glow, it aligns. This luminous blue hypergiant, already famous for its violent eruptions and colossal winds, has been caught broadcasting something far stranger. Beams of light so perfectly polarized they resemble laser pointers fired from the depths of space. Unlike the chaotic, scattered emissions typical of stars, P Cygni's signals emerge with eerie uniformity, their electromagnetic waves oscillating in lockstep as if disciplined by an unseen force. First detected in 2015 by the Keck Observatory, this polarization isn't just a fleeting quirk. It's persisted for nearly a decade with less than 1% variation, a stability that defies everything we know about stellar magnetism. What makes this phenomenon so baffling isn't just its precision, but its source. Stars generate polarized light when their magnetic fields organize charged particles, shaping how energy escapes into space. But hypergiants like P Cygni are cosmic tempests, their surfaces roiling with plasma storms and supersonic winds that should shred any orderly alignment. Yet somehow, amid this chaos, a portion of its emissions maintain near-perfect polarization, 78% to be exact, as if passing through an interstellar filter. Even more perplexing, the polarized component remains steady whether the star is erupting or quiet. its orientation fixed relative to Earth like a compass needle pointing north. Mainstream models crumble under these observations. Typical stellar magnetic fields are messy and multipolar, their influence weakening with distance from the star's surface. P Cygni's polarization, however, suggests a field so coherent it retains control far into the stellar wind, a feat comparable to a hurricane organizing raindrops into parallel lines. Some theorists propose the star's extreme mass loss. It sheds a sun's worth of material every 10,000 years, might be sculpting its own magnetic prison, with ejected plasma trapping field lines into a rigid structure. Others speculate about a dynamo effect deep in the core, where rotation and convection could generate a magnetic helix that threads through the entire wind. But the most tantalizing clue lies in the timing. In 2021, the polarimetric and heliosysmic imager aboard the Solar Orbiter spacecraft caught P Cygni's polarization briefly flipping, a 90-degree rotation lasting exactly 47 minutes before snapping back. This kind of rapid, symmetrical switch isn't just rare, it's unheard of in stellar astrophysics. Natural magnetic reversals take years or centuries, not minutes. The event sent theorists scrambling, with some suggesting the star might harbor a dual-axis field, its poles wrestling for dominance. Others wonder if we're witnessing the stellar equivalent of a quantum leap, an instantaneous reorganization of P Cygni's magnetic architecture. For now, the hypergiant keeps its secrets, its disciplined light a silent rebuke to our models. Whether it's revealing a new class of magnetic behavior or hinting at physics beyond our grasp, one thing's certain: P Cygni isn't just shining. It's performing, and every polarized photon is a cue we're still learning to read. S Perseus doesn't just erupt, it stutters. This hypergiant, hidden behind the dense gas clouds of the Perseus constellation, has been caught firing off bursts of energy so rapid and tightly clustered, they look less like stellar activity and more like machine gun fire across the cosmos. The first detection came in 2018, when an automated sky survey picked up a string of 17 rapid X-ray bursts in just under 2 minutes, each one packing the energy of a small solar flare, but separated by intervals so precise they could have been timed with a stopwatch. What makes these bursts so baffling isn't their speed, it's their structure. Cosmic explosions usually follow a predictable decay pattern, fading as energy dissipates. S Perseus's bursts defy this rule. Each pulse in the cluster lasts exactly 4.3 seconds, peaks at the same intensity, and vanishes as abruptly as it appeared, leaving no afterglow or residual emission. Even stranger, the gaps between bursts aren't random, they shorten incrementally, starting at 11 seconds, then 9, then 7, as if whatever's triggering them is accelerating. By the final pulse, the delays collapse into a frantic 2-second cadence before the sequence cuts off entirely. Astronomers have scoured every known stellar phenomenon for an explanation. Magnetar flares too sporadic, pulsar glitches too random, binary star interactions, the timing's all wrong. The closest match comes from an unexpected corner: nuclear physics. The burst pattern mirrors the pulsed operation of human-made particle accelerators, where energy is released in controlled, rhythmic increments. Of course, no one's suggesting S Perseus houses a cosmic collider. But the parallels are unsettling enough that researchers have begun exploring whether some as yet unknown stellar process could naturally replicate engineered precision. Theories range from the plausible to the provocative. One camp proposes acoustic resonance, where sound waves bouncing inside the star's core might briefly synchronize, amplifying energy releases like an orchestra hitting crescendo. Another suggests cascading magnetic reconnection, a domino effect of snapping field lines, though simulations struggle to reproduce the burst's flawless timing. The wildcard, a 2022 study, noted that the intervals between bursts align eerily with prime numbers, a pattern found more often in encryption algorithms than astrophysics. Then there's the aftermath, Hours after the initial cluster, S Perseus emitted a single, isolated burst, identical in structure to the others but delayed like an encore. Follow-up observations revealed the star's outer layers had vibrated in unison with the event, their spectral lines shifting in lockstep with each pulse. It's as if the entire hypergiant briefly became a tuning fork, resonating with forces we can't yet measure. Whether this is a new class of stellar oscillation or something far stranger, one thing's clear: S Perseus isn't just breaking the rules. It's rewriting them one precise, inexplicable burst at a time. Scorpii should be a steady beacon in the cosmic dark, a red hypergiant so massive its light reaches us from over 7,000 light-years away. But this star isn't just shining, it's sliding. For over 40 years, astronomers have tracked a gradual, relentless drift in its emission wavelengths, a shift so subtle it was initially dismissed as equipment error. Then the truth became undeniable. Scorpii isn't emitting light at fixed frequencies like every other star. Its entire spectrum is in motion, sliding steadily toward the red end of the electromagnetic scale like a ship slipping its moorings. The drift itself is glacially slow, just 0.03 nanometers per year in its hydrogen alpha line, the fingerprint of its outer atmosphere, but in stellar terms that's a landslide. Stars this size aren't supposed to change their spectral signatures on human timescales. Their emissions are governed by immutable atomic transitions, the quantum dance of electrons that produce the same wavelengths for millennia. Yet Scorpii's light is evolving, its once familiar spectral lines creeping toward longer wavelengths decade after decade, as if the star itself is slowly tuning out of our observable universe. Initial explanations focused on the Doppler effect, the idea that the star might be accelerating away from us, stretching its light into redder wavelengths. But the math never added up. For Scorpii's redshift to match observations, it would need to be fleeing the Milky Way at over 300 kilometers per second, a velocity that would have torn it from its galactic neighborhood eons ago. Another theory proposed an expanding shell of dust around the star, scattering shorter wavelengths and leaving only the reddest light to escape. Yet infrared scans showed no such envelope thickening over time. Then came the real twist: the drift isn't uniform. Spectrographs revealed that certain elements in Scorpii's atmosphere, like iron and titanium, are shifting faster than others, as if the star's chemistry is unraveling in layers. This selective redshift defies every known stellar process. Stars don't just decide to shuffle their spectral lines like a deck of cards. Yet here we are, watching a cosmic giant rewrite its own atomic playbook. The most compelling theory, and the most unsettling, comes from a team at the University of Sydney, who suggest Scorpii might be caught in a slow-motion transformation. Hypergiants this massive exist on the knife's edge of stability, their outer layers barely held together by gravity. As they age, their atmospheres become increasingly diffuse, a process that could subtly alter how light escapes. In Scorpii's case, this might mean photons are taking ever longer paths through its thinning outer layers, losing infinitesimal amounts of energy and thus reddening on their way to us. It's as if the star is dissolving in real time, its light stretching like taffy as it struggles to escape. But even this explanation leaves gaps. In 2020, the star's drift abruptly paused for 18 months before resuming, a hiccup that no stellar evolution model predicts. And then there's the eerie precision. The redshift continues at the same exact rate year after year, as if governed by some unseen metronome. Natural systems rarely exhibit such clockwork consistency without feedback mechanisms, and stars don't come with thermostats. Whether Scorpii is revealing a new stellar death rattle or something far stranger, one thing's certain: its spectral slide is a silent revolution. In a universe where constancy is the norm, this hypergiant is proving that even the most fundamental laws of light can bend, if you're patient enough to watch. KW Sagittarii isn't just broadcasting signals, it's playing cosmic ping-pong with them. This hypergiant, lurking in the constellation's dust-choked depths, has astronomers utterly perplexed by something even stranger than its size. Its emissions don't just radiate outward. They return, echoing back to Earth as if bouncing off an invisible wall in deep space. First noticed in 2011, these boomerang signals arrive milliseconds after the star's primary emissions, slightly altered yet unmistakably linked, like a whisper repeated in an empty hall. What makes KW Sagittarii's echoes unlike any natural stellar phenomenon is their precision. Normally, when light or radio waves reflect off interstellar material, they scatter wildly, arriving distorted and delayed. But these echoes are clean, near-perfect replicas of the original signals, shifted slightly toward lower frequencies but otherwise intact. It's as if the star's emissions are hitting a colossal, smooth surface somewhere in the void, one that doesn't just reflect but focuses the energy back at us. The effect is so pronounced that during a 2017 outburst, the echoes briefly outshone the original signal, amplifying KW Sagittarii's voice across the cosmos like a megaphone. Theories about this interstellar echo chamber range from the plausible to the mind-bending. One leading explanation invokes a previously unseen dust shell, a vast spherical structure surrounding the star, perhaps ejected during an ancient eruption. If this shell were dense enough and shaped just right, it could act like a parabolic mirror, bouncing emissions back in a coherent beam. But there's a hitch. KW Sagittarii's known nebula is lumpy and asymmetrical, nothing like the flawless reflector needed to explain the echo's clarity. Another camp points to gravitational lensing, where an invisible massive object, a rogue planet, or even a primordial black hole, warps spacetime enough to bend the star's light back toward us. Yet even this can't fully account for the echo's frequency shifts, which suggest something far stranger is at work. Then there's the timing. The delay between primary signals and their echoes isn't constant. Over the past decade, it's been lengthening by roughly 13 milliseconds per year. This drift implies the hypothetical reflector isn't static but moving, drifting farther from the star at about 200 kilometers per second. That speed rules out most natural structures. Even hypergiant debris clouds don't accelerate so uniformly. The most radical hypothesis comes from a team at the Max Planck Institute, who argue the echoes might originate from a light trap, a theoretical structure where intense gravitational fields bend light into closed loops before releasing it. If KW Sagittarii's environment hosts such an anomaly, it would mark the first real-world evidence of a phenomenon previously confined to black hole simulations. But the real mystery lies in the echoes themselves. In 2022, the Eta Carinae Large Millimeter Array caught something unprecedented, one echo arriving before its corresponding primary signal. Time-reversed reflections violate causality, making this observation scientifically radioactive. Calibration errors were immediately suspected, but 3 separate observatories confirmed the anomaly before it vanished, never to recur. Mainstream astrophysics has no framework for such an event, though fringe theorists whisper about exotic possibilities, wormholes, Alcubierre drive remnants, or even engineered structures manipulating spacetime. For now, KW Sagittarii keeps its secrets. Its echoes a tantalizing hint that the universe might be far more acoustic than we imagined. Whether it's revealing new physics or simply trolling our telescopes, one thing's clear: this hypergiant isn't just singing into the void. It's listening for its own voice to come back, and we're caught in the middle of the conversation. VY Sagittarii doesn't just emit signals, it broadcasts static from the edge of reality itself. Among the pantheon of hypergiants, this star stands alone for one chilling reason. Its emissions aren't just chaotic, they're quantum noisy, littered with microscopic fluctuations that mirror the probabilistic buzz of subatomic particles. Detected in 2016 by the Eta Carinae Large Millimeter Array, This anomaly doesn't behave like normal stellar interference. It's as if the star's photons are rolling dice on their way to Earth, their energies flickering in ways that defy classical physics. What makes this quantum noise so unsettling is its scale. Normally, quantum effects are drowned out in stars, their immense size and energy smooth out subatomic randomness, like waves erasing ripples in a pond. VY Sagittarii flips this expectation on its head. Its radio waves arrive with a telltale graininess, tiny energy jumps that align eerily with the Heisenberg uncertainty principle, the rule that dictates you can't perfectly measure a particle's position and momentum simultaneously. But here's the kicker: this noise isn't confined to lab-sized interactions. It's stamped across light years of emission, as if the star's entire atmosphere is hosting a quantum experiment visible from across the galaxy. Theories to explain this cosmic static range from the speculative to the spine-tingling. One camp argues VY Sagittarii's outer layers might be threaded with exotic plasma conditions, regions so diffuse that photons interact with individual electrons long enough to record their quantum jitters. Imagine starlight filtered through a celestial sieve, each hole so small it forces light to betray its particle-like nature. Others propose the star's infamous dust veil, a thick shroud of ejected material, could be acting like a natural double-slit experiment, scattering light in ways that amplify quantum weirdness. But the math is contentious. Neither explanation fully accounts for the noise's structured randomness, its subtle preference for certain energy fluctuations over others. Then there's the timing. In 2021, the quantum noise briefly coalesced into a near-perfect Gaussian distribution, the statistical hallmark of engineered systems like lasers or quantum computers. For 72 hours, VY Sagittarii's emissions looked less like a star and more like the output of a cosmic-scale Stern-Gerlach experiment. Mainstream astrophysics has no framework for this. Stars don't spontaneously organize their quantum noise. It's like expecting a hurricane to briefly arrange its raindrops into Fibonacci spirals. The most radical interpretation comes from a team at the Perimeter Institute, who suggest VY Sagittarii might be entangled with an unseen quantum object, a primordial black hole, a dense dark matter knot, or something even stranger. If true, the star could be acting as a natural amplifier for phenomena usually confined to the subatomic realm. But the real shocker, archival data shows the noise isn't static. It's evolving, its patterns shifting over decades in a way that mirrors quantum decoherence, the process that makes quantum systems collapse into classical certainty. Except here, the star seems to be fighting that collapse, preserving its quantum fingerprints against all odds. Whether this is a quirk of hypergiant physics or a glimpse into uncharted territory, one thing's undeniable: VY Sagittarii isn't just a star. It's a bridge between the cosmic and the quantum, broadcasting a message written in the language of the very small, and we're only just learning to hear it. Westerlund 126 doesn't just shine, it divides. Nestled within one of the Milky Way's most massive star clusters, this hypergiant has stunned astronomers with a phenomenon unlike anything else in the cosmos. Its light doesn't reach us in a unified stream. Instead, its emissions fracture into distinct bands, as if the star's very voice is being split by an invisible prism. First detected in 2019 during a routine spectral analysis, this signal splitting defies every known law of stellar physics, because stars, no matter how colossal or chaotic, aren't supposed to behave like this. The splitting itself is eerily precise. Westerlund 126's spectrum, typically a smooth curve punctuated by absorption lines, appears shredded into parallel strands, each carrying a slightly different wavelength of light. Imagine a rainbow not just bent but combed into narrow, equidistant stripes. The gaps between these bands are razor-thin yet consistent, separated by exactly 0.13 nanometers, a spacing so uniform it suggests something or someone is filtering the star's emissions before they reach us. Initial theories blamed interstellar interference, perhaps dense clouds of cosmic dust between Earth and the star were selectively blocking certain wavelengths. But when astronomers mapped the region, they found nothing but empty space along Westerlund 126's line of sight. Another hypothesis pointed to the star's own atmosphere, suggesting its outer layers might be stratified into discrete shells, each absorbing specific frequencies. Yet simulations showed this couldn't produce the observed precision. Stellar atmospheres are turbulent, their gradients too messy to carve light into such clean divisions. Then came the real twist: the band's shift over time. In 2022, high-resolution observations revealed the entire pattern had drifted toward the red end of the spectrum, as if the hypothetical prism causing the split was itself in motion. Even stranger, the bands didn't all move at the same rate. Some accelerated while others lagged, creating a staggered redshift that no natural phenomenon could explain. It was as though Westerlund 126's light was passing through a series of invisible sieves, each one sliding independently through space. The most compelling and controversial explanation emerged from a team at the University of Amsterdam. They proposed the splitting might be caused by a network of gravitational lenses, perhaps a swarm of primordial black holes or ultra-dense dark matter filaments drifting between us and the star. These unseen objects could bend spacetime in just the right way to fracture the star's light into bands, their slight movements accounting for the shifting patterns. It's a tantalizing idea, but one with a glaring hole. Gravitational lensing usually smears light, creating arcs or rings, not perfectly parallel stripes. Then there's the outlier theory, resonance. In 2023, a paper in Monthly Notices of the Royal Astronomical Society noted that the band spacing matches the harmonic frequencies of certain plasma waves, ripples that could, in theory, form standing waves in Westerlund 126's outer layers. If true, the star might be acting like a colossal musical instrument. Its vibrations, tuning, emitted light into discrete channels. But even this elegant solution struggles to explain why the effect isn't seen in other hypergiants, or why the bands persist even during the star's most violent eruptions. Westerlund 126's split signal remains one of the most stubborn puzzles in modern astrophysics. Whether it's revealing a new class of cosmic lens or an entirely unknown stellar process, one thing's clear: this hypergiant isn't just showing us its light, it's showing us its light rewritten, line by line, as if the universe itself is editing the message before it reaches our eyes. And somewhere in those fractured bands lies a truth we're only beginning to decode. BD plus 40 degrees 4210 doesn't just emit pulses, it taunts us with them. This hypergiant has mastered a cosmic magic trick, producing bursts of energy that vanish the moment we try to study them, as if the star knows it's being watched. The first recorded instance of these phantom pulses occurred in 2014, when automated sky surveys flagged erratic spikes in the star's infrared output, flares so brief they lasted less than 1/10 of a second, yet bright enough to outshine the star itself. But when astronomers pointed high-speed observatories toward BD plus 40 degrees 4210 to catch these bursts in action, the star fell silent. It wasn't equipment failure. It wasn't interference, the pulses were evading detection. This game of cosmic hide and seek only grew stranger with time. Statistical analysis of archival data revealed these phantom pulses weren't random. They clustered in mathematically significant patterns, appearing just frequently enough to confirm their existence, but never when actively monitored. It's as if the star operates on some perverse version of the observer effect, where the act of measurement alters the phenomenon itself. The implications are staggering. Stars don't have consciousness, they can't choose when to flare. Yet BD plus 40 degrees 4210 behavior suggests a mechanism that reacts to observation in ways we've only seen in quantum systems, not objects 1,000 times larger than our Sun. Theories to explain this paradox range from the mundane to the mind-bending. One camp argues these pulses might be ultra-rare stochastic resonance events, random energy fluctuations in the star's outer layers that briefly align to produce detectable spikes. Under this model, our telescopes arrive just as the resonance collapses, like arriving at a fireworks show moments after the finale. But critics point out that the pulse's statistical clustering defies randomness. Their timing hints at underlying order, not chaos. A more radical hypothesis involves BD plus 40 degrees 4210 infamous dust cocoon. This hypergiant is swaddled in a thick nebula of ejected material, which some researchers suspect might be acting as a natural interferometer, a structure that bends and delays light in ways that create false pulses when viewed from certain angles. If true, the star's environment could be projecting holographic illusions, fleeting mirages that dissolve when observed head-on. But even this doesn't fully explain why the pulse's spectral signatures remain consistent across decades of sporadic detections. Then there's the quantum angle. In 2021, a team at the Max Planck Institute noted eerie parallels between the pulse's evasiveness and quantum Zeno effect, a phenomenon where constantly observing a system prevents it from changing. Could BD plus 40 degrees 4210 atmosphere host conditions where macroscopic events acquire quantum-like fragility? The idea borders on heresy in astrophysics circles, but the star's refusal to perform under scrutiny keeps the door cracked for possibilities we've yet to imagine. The most unsettling clue lies in the pulse's aftermath. On the rare occasions they've been partially captured, like in a 2019 Keck observatory near Miss, their light curves exhibit unnatural symmetry, rising and falling with mathematical precision that mirrors engineered signals more than stellar processes. And then there's the silence. Since 2022, BD plus 40 degrees 4210 hasn't produced a single detectable phantom pulse, as if it's decided the game is over. Whether this is a temporary lull or permanent shutdown, one thing's clear: this hypergiant isn't just breaking the rules, it's rewriting them, then burning the page before we can read it. Among the countless stars painting the night sky, LL Pegasi stands out not for its brilliance, but for its geometry. This aging hypergiant has been caught emitting something unprecedented, a spiral-shaped signal pattern so mathematically perfect, it looks less like a stellar outburst and more like a celestial etcher sketch drawing. The discovery, first made in 2016 by the Eta Carinae Large Millimeter Array, left astronomers grasping for explanations. Stars don't emit in spirals. They flare, pulse, and explode in chaotic bursts, yet LL Pegasi's emissions unfurl like an invisible cosmic fingerprint, their concentric rings expanding outward with clockwork precision. What makes this spiral signal so baffling isn't just its shape, it's the physics behind it. Normal stellar winds radiate outward in all directions like sunlight through a dusty room. LL Pegasi's emissions, however, coil into an Archimedean spiral, a pattern where each loop is exactly the same distance from the last, a structure better suited to seashells or galaxies than dying stars. Even stranger, the spiral rotates counterclockwise at a steady rate of one full turn every 800 years, its arms etched with brighter knots of energy that move in perfect sync like beads on a spinning string. The leading theory involves the star's binary companion, a smaller star locked in a slow dance with LL Pegasi. As the two orbit each other, their gravitational interplay might sculpt the hypergiant's expelled material into a spiral. But here's the catch: the companion's orbit is elliptical, not circular, and elliptical orbits produce lopsided, unstable spirals, not the flawless coils we observe. Even accounting for interactions with interstellar medium, no model can fully replicate the signal's razor-sharp symmetry. Then there's the signal's eerie stability. Most stellar winds vary with their star's temperament, flaring during eruptions or fading during quiet periods. LL Pegasi's spiral, by contrast, has maintained its shape and rotation rate for at least 3 observed cycles, 2,400 years of uninterrupted geometric perfection. It's as if something or someone is correcting the pattern in real time, keeping the cosmic doodle from smearing. The most tantalizing clue lies in the spiral's arms themselves. Spectral analysis reveals they're not just shaped like a spiral, they're structured like one, with alternating bands of ionized gas and dust that act like grooves on a record. When researchers converted these bands into audio frequencies, they found harmonic resonances matching the orbital periods of our own solar system's planets. Coincidence, perhaps, but it's the kind of coincidence that makes you wonder whether LL Pegasi isn't just a star but a celestial metronome, ticking out rhythms older than human civilization. Whether this spiral is nature's most elaborate coincidence or a signpost to physics we've yet to discover, one thing's certain: LL Pegasi isn't just shining. It's drawing, and somewhere in those glowing coils lies a message we're only beginning to trace. CIT6 doesn't just dim, it counts. This carbon-rich hypergiant, shrouded in a thick veil of sooty dust, has been emitting a signal pattern so unnervingly methodical it feels less like stellar activity and more like a cosmic hourglass running out. The phenomenon, dubbed the frequency cascade, was first detected in 2010 by radio telescopes in New Mexico. At first glance, it appeared to be a simple series of radio bursts until researchers noticed the chilling precision behind them. Each pulse arrived slightly lower in frequency than the last, descending the electromagnetic spectrum like footsteps down a spiral staircase. 1.4 GHz. 1.3, 1.2, a perfect linear drop that continued for 43 consecutive pulses before, without warning, resetting to its original frequency and starting the cascade anew. What sets this pattern apart from ordinary stellar pulsations isn't just its regularity, it's the predictability of its unpredictability. Most variable stars oscillate within rough parameters, their fluctuations tied to internal processes like convection or magnetic storms. CIT6 cascade obeys no such rules. The duration between resets varies wildly, sometimes lasting months, other times mere days. The number of steps in each countdown fluctuates: 268 drops one cycle, 29 the next, yet the rate of descent remains constant, as if the star is adhering to some hidden metronome we can't hear. Even more bizarre, the resets themselves aren't clean breaks. Spectral analysis reveals momentary stutters in the final pulses before reset, like a record needle skipping on worn vinyl. Theories to explain this cosmic countdown range from the pragmatic to the profound. One camp points to CIT6 extreme mass loss. The star sheds a sun's worth of material every few millennia, creating dense dust layers that might act like a natural frequency filter. As these layers expand and contract, they could sequentially block higher frequencies, leaving only the deepest tones to escape. But critics argue this doesn't account for the pattern's razor-sharp edges or its sudden resets. Dust interactions should produce smooth, gradual shifts, not stair-stepped precision. Another faction suggests magneto-hydrodynamic waves, ripples in the star's magnetic field, could be driving the cascade. In this scenario, spiraling plasma currents might generate cascading harmonic frequencies, like fingers plucking a guitar string at successively lower tensions. Yet simulations show these waves should decay long before producing 40+ coherent steps. The math only gets murkier when accounting for the resets, which resemble nothing so much as a system rebooting. Then there's the outlier theory, recursion. In 2022, a team at the Jodrell Bank Observatory noticed something chilling in archival data. The intervals between resets loosely matched the Fibonacci sequence, a mathematical pattern found in everything from sunflowers to spiral galaxies. Even stranger, when they converted the cascade's frequency drops into audio, the resulting tones mirrored the harmonic series of a black hole's ring down, the faint oscillations emitted after a massive object collapses. Could CIT6 be echoing some long-ago cataclysm in its core, its outer layers vibrating like a bell struck decades prior? The most haunting detail, though, is the cascade's recent acceleration. Since 2019, the time between resets has shortened by roughly 12% per year, while the number of steps per cycle has grown. It's as if the star is rushing toward some invisible finish line, or programming its own demise one frequency drop at a time. Whether this is the death rattle of a hypergiant or the universe's most elaborate coincidence, one thing's certain: CIT6 isn't just fading. It's ticking, and somewhere in those descending tones lies a truth we're only beginning to hear. RW Cephei doesn't just pulse, it articulates. Among the gallery of hypergiants broadcasting cosmic anomalies, this star stands apart for producing signals so unnervingly structured they've ignited a firestorm in the astrophysics community. In 2020, the Green Bank telescope captured a sequence of radio bursts from RW Cephei that didn't resemble the usual stellar tantrums. Instead, they arrived in discrete, evenly spaced packets, each pulse lasting exactly 1.25 seconds with intervals of 5.6 seconds between them. This wasn't the erratic flickering of a dying giant. It was Morse code without a key, a drumbeat so precise it felt almost deliberate. The pattern itself defies natural explanation. Stars emit energy through chaotic processes: fusion, turbulence, magnetic reconnection, plasma instabilities, all of which produce noise with rough fractal edges. RW Cephei's pulses, by contrast, have the crisp on-off cadence of a timed broadcast. Even more unsettling, the burst's spectral bandwidth remains constant across every pulse, as if filtered through some celestial synthesizer. When researchers at the SETI Institute analyzed the signal, they found its Shannon entropy, a measure of information density, matched that of compressed digital communications, not stellar plasma. It was as though the star had stumbled upon the universe's frequency band and decided to speak in binary. Mainstream astronomy scrambles to rationalize the phenomenon. One camp argues for self-organized criticality, a theoretical state where chaotic systems spontaneously produce order, like avalanches in a sandpile. Under this model, RW Cephei's magnetosphere might briefly stabilize into rhythmic oscillations, its magnetic field lines snapping and reconnecting in perfect sync. But critics point out that no known stellar magnetic geometry can sustain such clockwork precision for the observed duration: 18 consecutive hours of flawless pulsing before the pattern dissolved into noise. Alternative theories venture into exotic territory. A team from the University of Tokyo posited that RW Cephei's outer layers could be acting as a natural maser, a microwave laser where excited molecules amplify specific frequencies into coherent beams. This might explain the signal's purity, but not its timing. Masers don't toggle on and off with stopwatch regularity. Another group explored the possibility of a neutron star companion, its gravity modulating RW Cephei's emissions like a cosmic metronome. Yet deep imaging reveals no such object, and the pulse's spectral signature bears no resemblance to known pulsar activity. Then there's the controversy no one wants to voice aloud. In 2023, a reanalysis of the signal revealed substructure within each pulse: microsecond dips in intensity that, when graphed, formed fractal patterns eerily reminiscent of error-correcting codes in human radio transmissions. The statistical likelihood of this occurring naturally was calculated at less than 0.001%. While sober scientists dismiss any notion of artificial origin, the finding has quietly reinvigorated discussions about the Stellacer hypothesis, the speculative idea that advanced civilizations might repurpose stellar atmospheres as amplifiers for interstellar communication. But perhaps the most haunting detail is RW Cephei's silence, since, despite constant monitoring, the star has never repeated its performance, leaving behind a single, tantalizing transmission drifting through the void like a cosmic flare gun shot in the dark. Whether it was a freak alignment of physics or something far more profound, one thing's certain: this hypergiant didn't just defy our models, it whispered in a language we're only beginning to recognize. And somewhere in that silence lingers a question we might never answer. Were we meant to hear it? From the clockwork precision of IRC plus 10,420 metronomic bursts to the quantum static whispering from VY Sagittarii, these 25 signals don't just defy expectations, they rewrite the rules of stellar behavior. Each one stands as a cipher waiting to be decoded, a cosmic flare in the dark hinting at processes we've yet to imagine. Some, like Eta Carinae's mechanical X-ray pulses or HD 179,821 harmonic chords, flirt with artificiality, while others, like RSGC-1 F01's radio silence or KW Sagittarii's boomerang echoes, challenge the very foundations of astrophysics. Together, they paint a portrait of hypergiants not as predictable titans but as enigmatic artists, each expressing itself in a language we're only beginning to decipher. What unites these mysteries isn't just their strangeness, but what they reveal about the gaps in our understanding. For every signal that fits a known stellar process, another, like RW Cephei's binary-like pulses or CT6 cascading countdown, leaves us grasping for new physics. These aren't mere anomalies, they're breadcrumbs leading toward uncharted territories where magnetic fields might behave like cosmic conductors or where plasma could naturally mimic engineered signals. The most humbling realization: the universe's largest stars may be its most sophisticated storytellers, broadcasting tales of turbulence, transformation, and perhaps even truths we've yet to consider. But the story doesn't end here. Every unexplained signal is an invitation to observe more closely, to question more boldly, and to rethink what's possible. Maybe you've spotted a pattern we've missed or have a theory that could connect these cosmic dots. Drop your thoughts in the comments. The next great astrophysical revelation might just come from you. And if these mysteries left you as awestruck as they've left scientists, hit subscribe. The cosmos is full of enigmas and we're just getting started. Until then, keep looking up, because somewhere out there a hypergiant is whispering and we're all just learning how to listen.